Hello there. My name is George Comstock. I'm the Marketing and Sales VP here at Network General Corp. We're going to put together a videotape here for our salespeople, which is designed to show some of the advantages of the Sniffer over competitive products in the field. The competitive products that we'll be looking at include the Hewlett-Packard 4972A, the Exelan 5500, and the Spider Monitor P200. We have these three machines available for us in this classroom, and our president, Dr. Harry Saal, will take them through their performance characteristics and compare them with the performance of the Sniffer. We'll use two video cameras for doing this homebrew videotape. One of the cameras will be focused on the screens of the three competitive machines, and the other camera will be used to record Harry's movements and talk. Also, we will have a Sniffer whose screen is being projected on the wall, and we'll pick up that screen with the camera that's being used to record Harry's operations. Now, the talk will focus on one of the most important characteristics of the Sniffer, an area where we have a very significant competitive advantage, and that's the area of decoding the protocol content of the frames that are captured from a network. By decoding the protocol content, we can provide our user with much more usable and useful information and displays of that information to assist him in tracking down the underlying causes for problems that he is experiencing or that he may in the future encounter, which are there but haven't yet shown themselves in full vigor. This decoding capability is at a peak in the Sniffer, and as you'll see from the demonstrations, it's handled in a much more primitive fashion in the other machines. So when you, our salesperson, are out demonstrating the Sniffer to a prospect, this is an extremely valuable area to him, potentially, and you should really call his attention to the fact that we do provide him with all kinds of extra information in this region as compared with the competitive machines. With that, then, I'll turn the session over to Dr. Harry Saal, our president, and count on him to do his usual fine job of presenting the comparisons. And here's Harry Saal.
Okay, George, thank you very much for the introduction. Today what we're going to do is to look at four different protocol analyzers, the Sniffer, and three of its main competitors, the Hewlett-Packard 4972, the Analyzer 5500, and the Spider Monitor P200. Now, the setup that we have here today is an interesting one. All four of these network analyzers are connected to the same Ethernet, and we have a fifth station also connected to that Ethernet, which has the capability of playing back a previously captured sample of real data from some other Ethernet and simulating in real time all the bits and bytes that travel on that network, so we can then compare side by side these four machines on precisely the same data. Now, in fact, let me say a few words about some of the things that we're not going to compare. We're not going to talk about the weight of these four units. We're not going to talk about the size of these four units, differences in the nature of the screens or disk capacity. Those are pretty relevant issues. But today we're going to focus on only one particular factor, namely, how do these products help me understand what is going on a network? They're all billed as protocol analyzers, and the job that we're going to look at is their ability to analyze a situation, a problem situation, on a real-world lens. Let me give you one idea. I'll briefly go through, before we do the comparison, with the general kind of capabilities that the Sniffer has. Most of you are familiar with it, but let's just set the stage with that And the objective will be then to see to what degree the other products provide that similar kind of capability. So what I'll do now is put the machine in capture mode. And George, if you'll play back onto the screen the trace called TCP/IP. It's a collection of typical TCP/IP network activity with a variety of different protocols going. We'll collect that and watch what happens on the screen here as we see that data. First thing we'll do is some idea of the activity, what stations are using the network, their IDs, the amount of traffic back and forth, fairly rich environment. But in fact, the part that we want to look at is not so much the runtime displays, but rather the protocol analysis. All I have to do is press one key, F3. The system has taken the packets that it's collected and showing me, in this case, 20 lines at a time. It's explaining to me what has happened on the network. For example, I can see here that the first frame is the protocol NFS. It was a command, the letter C, to look up a file whose name was hostinfod.o. And I'm going to ask a very simple question. Did that file exist or not? Pretty easy to tell. The next line is a response coming back to that same station. No such file. What has this taken us? 5 seconds? Less? To appreciate what those two packets meant without having to look at any hex bytes or data, selecting any options. We can immediately see that there is some NFS activity here. In fact, we can read it like a book. There's a lookup command, no such file, and then the third packet, in fact, was a create command. That file didn't exist, so the user went out and created it. Here we see other kinds of activity. Notice in addition to NFS, we have Telnet, we have TCP, we have Domain Name Service, DNS. And again, the sniffer makes it very easy to go and look and see more information. For instance, let's see just the Telnet activity. I would like to study Telnet activity on this network. I can just press one function key, F6, F to go to my filters group and select a protocol filter. And the one we'd like to look at is, say, Telnet. I can press the letter T several times until I come to the activity Telnet, the entry Telnet. And now I can see just the Telnet frames on the network. Let's make one more change. We'll go and set the two-station format mode on the sniffer so that one station will be on the left-hand side of the screen, the other on the right. Okay? Let's review now what we've done. We've captured some data. We made a quick observation. We saw some NFS data. We saw some Telnet data. We decided we want to focus on the Telnet traffic. We selected it. And now here we can see the Telnet activity. Here is the station sending a character. C is sending it to a host. R is the response. Notice the letter that was being sent was the letter U. The echo that came back was the letter U. We might ask other questions. How fast was the response time of this network? Again, we just read that off. The response time was 0.04 seconds. Let me move the cursor down there. The time between packet 5 and packet 4 was 0.04 seconds. That's how long it took the host to echo. Let's take a look now at packet 23. There's a response frame. What was the response time of the host? 0.04 seconds. Here's another frame. What was its response time? 0.07 seconds, 0.05 seconds, 0.05 seconds. Basically, within a 20th of a second, this particular host is responding. We can immediately get an observation that it's responding very well and very quickly. Notice here, for example, interestingly, we can get some idea of the user's delay time as these characters are entered. Notice between the time that this character came back, there was about a 1 second delay before another key was pressed. Then there was a 1/5 of a second delay. This is probably a user actually pressing the keys, and we're seeing the user reaction time over there. We can see some other interesting things. Here, for example, what was the character the user pressed? It was not a letter U, it was a ASCII hex character, the code 7F. What's a 7F character? That's the ASCII code for delete. He pressed the delete key on his keyboard. What got echoed? Notice here on the next line, it's not the 7F character, but in fact, a different ASCII code, 08. What is 08? It happens to be a backspace key. This is an interesting example of where we can see here something is being processed by the host. It's doing some character substitution during translation. A perfect example of the kind of problems that occur. The user might hit delete, and perhaps the wrong character was being echoed, and so on. Down here, for example, the user presses carriage return line feed, 0D, 0A. What comes back from the host? These characters. Escape, left paren, left bracket K. That's a VT100 terminal sequence. Oh, what are these two characters? 00, 00. Why are there two null characters? In fact, there are more null characters here. Notice there are several null characters that were being sent before the carriage return line feed. Perhaps those null characters ought to be there. Perhaps those null characters aren't there. But very, very quickly, we're seeing what's going on, how the network is being used, and we can go and do some analysis of them. Let's go back. Let's look at the NFS protocol instead of Telnet protocol. And just as easily, I can go and select NFS and deselect Telnet. And here we are again, looking at that same screen, but in a similar mode. Look up a file, no file found, create a file, read OK, read some data from that file. No data was returned. He tried to read 4,000 bytes from a file. No data was returned. The program then wrote 4,096 bytes at location 0 to that file, and so on. We can ask some interesting questions. For example, this file was created here. Let's say we need to know more information about the file, such as the particular group of users that can access that file. That information is not here at this very high level summary view. So for certain other information in the sniffer, we have to go and look at the detail view. We'll look at this frame number 3, and I'll turn on an option of a detail window. Let me zoom it out. And what we find out is that this file was being created. And again here, there's a mode which is being specified, and there's a very simple description that says that the owner is being permitted to read and write in the file. And in fact, the group of users that access this file may also read and write, and in fact the general public may read and write into that file. If I go to the next frame, which is the reply from the file server has gone in and added some additional information, giving such things as when this file was created, the access time, the last modification time of this file. Of course, they're all the same time since the file really hasn't been used yet. And here it says that this was on December 10th, 1986 in GMT. This is then a complete decode of every single option in a Sun NFS create file response frame. I needn't tell you that in addition, the sniffer has already gone ahead and analyzed all the other protocols associated with this packet. The Sun remote procedure call level, the UDP level, the IP level above it, and before that, the Ethernet level. All that information is available. And what I'd like to point out are a few things about the nature of this information. Much like we looked at the summary screen, the system is designed to make it possible for you to understand this information without really knowing much about the details of the protocol. For instance, here, this file was accessed December 10th, 1986 at 7:20 in the PM GMT time. How did the sniffer know that? Where did that information come from? Well, we can find out by going to the hex. In the hex window, we can see that if I put the highlight at this level in the detail window, that these bytes here somehow decode into that access time. If we are looking, rather than at a Sun NFS file, at a frame from, say, the SMB interpreter, you know that there's also a creation time associated with SMB files. There is a creation time associated with files from a Novell protocol. Each of them has a timestamp like this, and in fact, each of them is encoded totally differently. The sniffer has an encyclopedic knowledge that basically presents that information to you in a very easy to understand form, so that you don't have to understand the mysteries of the hex, find the reference information, and so on. Goes one step beyond that. If we look at the summary line, notice here, for instance, we see an NFS write command. The sniffer stylistically maintains the integrity of that analysis to promote ease of learning. If this was an SMB write command, in fact, it would say SMB, command, file number, write 4,000 bytes at location 0. What do you think it would say if this were a Novell core protocol write command? It would say Novell core protocol, NCP, command, write, and so on. That similarity, that ease of use, is rather unique in making it possible to start at this level on a protocol that one is not necessarily familiar with and immediately understand the general properties of what's happening, what's going on from a very high level application point of view. We can do exactly the same thing if we like by going to the TCP level or lower levels, but we can now see really the ease of use is the main emphasis. The ease of understanding the protocol without having to guess, gee, I wonder what format it's being used in, I wonder what timestamp is being used. The same is true, notice here, in terms of the formatting of these packets. Okay? This information is being printed out as a timestamp. This information is a block size, is being printed out in decimal, because decimal is a natural number to use when you're printing out a block size. The mode of a Sun file, I believe, is printed in, would you believe, octal. I think is actually what's being used there. If I go up here, for instance, we'll see in the IP level that the source address is printed in a very natural internetwork IP style notation. Left bracket, a decimal number, dot, a decimal number, recognizable to anyone who knows how to read an IP level. Checksums are being presented in hex. Bits are being broken down into consecutive bit fields. The sniffer uses a lot of freedom in display and is not strapped to displaying things just in hex, just in ASCII, or just in decimal. A very rich, very natural approach. In fact, it goes one step beyond that. Notice here, there are some fields which are clearly decodes. This is decoding some field, version, length, type of service, and so on. Fine. There's more to it. For instance, here, notice it says header checksum equals C78A. That was taken from the packet. This small message correct implies that actually the sniffer has gone, has itself calculated the checksum and verified that this is indeed a correct value. There are other places, as we'll see, where other numbers here actually are strictly not in the packet themselves, but are being derived from the packet. In order to proceed, let's do the following. Let's go to the spider monitor, turn it on to capture data, and collect exactly the same data as we have on the sniffer. So we have it in performance mode. Wrong. We'll put the system into development mode. Press run, and now the system is awaiting the playback of the data. Notice while it's being collected, all we can see here is the number of the packet that's being accepted. There is no runtime display information as to what's happening. Can you scroll over to that? Now the buffer just filled up. The spider monitor can hold a maximum of 300 packets. It came to the 300th packet, and now it is displaying the frames. So basically for each packet, we have a packet number, a size, time from the beginning of capture, and time between the previous packet. There's a destination, which by the way can be either a hex number or a name, just as in the sniffer, a source, and a type field. 0800, shown in hex, followed by some more hex. Okay, again, let's compare that to the sniffer. Looking at packet 1, we see here, packet 1 in fact was an NFS packet. It decoded all the way up to the highest level, showed us the type of packet, as well as the source and destination address. Here we have delta time, notice 0.034, just like 0.035, and a frame number, but considerable decode at this level of the information. In fact, if I go back to the spider monitor and look at its options, I'll press the system key, trace key, and we're then decoding it with the hex protocol in medium form. Let me change this to short form and redisplay the same packets, just to give you an idea of what you can see. In this case, we see a few more packets on the screen, but again, the only information that's available are these fixed 4 fields: the size, time from the beginning of capture, time from the preceding packet, destination, source, and the ether type and hex. You'll see this is very reminiscent of what you'll find on the Analyzer product and the HP product. In the case of the sniffer, we can display time, we can display size. Time can be relative to any point at all in the trace, as well as the other fields. Let's go and change the display, because notice one thing it doesn't do is tell us anything about what these frames are, what their content is. Are there telnet frames here? Basically, you can't find out. Are there NFS frames here? Basically, you can't find out. Now, there are some other options in terms of its built-in decoders. Go back to the trace button, and I can say which decode to use. They have several built-in options. We were using the default one when you start up called hex. Let's change that. There's one called XNS. Okay, let's turn on the XNS decoder, and we'll change it to long form so we see all the XNS fields. I'll recall the packets, and here I see packet number 1 decoded an XNS packet, destination, source, checksum 4500, hasn't validated it, length 0B00, XNS control E6, packet type 5A, some other fields here. There's only one small problem. This is not an XNS packet. This is an IP packet. Here it says the ether type is 0800. Ether type 0800 is not XNS. I have to know ahead of time that this really is an IP packet. Consequently, I can very easily misread and misunderstand this data. Notice as well the data is presented in a not very well broken out form. So let's go back and assume that somehow we knew that this really is data from IP. We're using the XNS protocol. The next choice, there's a DECnet option. If I choose DECnet, again, by the way, it decodes it. It, in this case, decides not to decode more than the basic decode since it didn't have a DECnet protocol type. Here's the IP protocol. Okay, now I've told it, force a decode of this packet into IP form. Again, at this level, you have very little idea of what's going on. It's not showing you NFS packets. There's no way to select just telnet packets. So really this compares at best to not the style of decode we're just looking at with a very high-level view, okay, where we're showing this kind of context. Perhaps it's closer to looking at the detailed window. So let's look at the detail view of packet number 1 and compare it to the detail view. Notice here we automatically are looking at the sun level information, the highest level which we chose. Look up a file name and it's decoding it. That information is buried somewhere in this frame. Let's go to the top and notice here we see the destination, the source address, the size is the same. It's displayed both in decimal and in hex. The ether type, and here's the IP header. The first field that's decoded from IP is to say that the version of IP that's running is version 4 and the header length is 20 bytes long. Okay, let's take a look at how that information is presented on the spider monitor. The first thing we see after ether type 0800 is this field, VER/IHL equals 45. Actually, that is the byte that the sniffer is talking about. The very first byte of the packet happens to be, at this point, the hex value 45. But in fact, what that means is the first digit happens to be the version number, and the second digit, when multiplied by 4, is the number of bytes long, not being decoded. What's the next field? TOS equals 00. Let's look at the sniffer. Here it says type of service equals 00. The next byte, in fact, is the type of service byte, and here it's decoding all 8 bits of that. Apparently this is a routine packet with normal delay, throughput, and reliability. I assume if these bits weren't all zeros, then it would have told me that this was a express packet or had some other special handling that was due to it. That information is being told to me by the sniffer, which understands the protocols, rather than simply saying TOS equals 00. What does that mean? Again, if I come back to the spider monitor, we continue along. What you'll notice is that the length field here is shown in hex. The ID field is shown in hex. TTL equals FF. If we take a look at the sniffer, happen to notice a file, a location here called time to live, 255. Or down here, source address equals 36.53.0.33, a standard IP source address. What is that shown as on the spider monitor? Over here we can see IP source equals 24.35.00.21, a hexadecimal number that really is unrecognizable to anyone who uses IP. So what is the spider doing? Number one, it forces the user to select and make a stab at the kind of packet it is, and if you get it wrong, you may get some result or another. Secondly, in this case, the decoding that it's doing is very limited decoding of a few fields with simple hex decodes. And this seems to be a basic limitation of the product. That example, although not comprehensive, gives you a pretty good idea of the style of decoding that the Spider monitor provides. Very simple, very basic, assumes a lot of knowledge on the part of its user, probably something that someone who's a protocol developer might use, but really nothing that you could use to answer those fundamental questions that we saw in the sniffer. Who's using the network, what files are they accessing, and so on. Now we'll move on to the next popular product in the LAN analyzer field, the Hewlett-Packard 4972A LAN Protocol Analyzer unit. Let's go back, let's play the same trace back to the Hewlett-Packard 4972A. Okay, that unit is here, and what I'll do is put it in its mode where it's going to capture data, and I'm going to tell it by pressing a key, start monitor, and we have it in a mode where it's going to, I believe, collect every possible packet. Len, if you could play back the TCP/IP data. Okay. It's collecting it. It's showing us an occasional packet on the screen. It's scrolling by. Okay, the network has stopped transmitting, so I will stop the monitor. And now we're seeing a display of the packets in this form. Can you focus that? Zoom in. Doesn't have an intensity control or contrast control, the HP product. They get it right, you like it that way. This is not the Wendy's style product. It's the other philosophy. Get it right and it's their way. Okay, so what we're seeing here, we're seeing that this frame, number 1, was collected, and here's a destination address, a source address, the length of the frame in bytes, and something called filters matched. There are up to 16, I believe it is, some number of filters which the HP product can check to see whether or not certain bytes are present in each packet. And those filters have to be preset up ahead of time before you load the data in order for it to do its pattern matching. Nothing matched, but we told it to collect all the packets. And now it's showing us the destination address, the source address, and the frame length of that packet. We can go and seek more information. I can select the format of the packet. The product itself does not have any built-in decoders for TCP, XNS, DECnet, or anything. Okay? There's no such thing. What comes with the HP product is the ability for you to decide how you want to decode a packet. What does decoding a packet mean? Decoding a packet means knowing the length and offset and value of the fields in the packet. They've done you a favor, and they have what is called a utility disk that comes with the HP product for the LAN Protocol Analyzer, which says, among other things, that this user's guide and its associated disk are a set of unsupported tools for use with the LAN Protocol Analyzer. They were developed to help the HP 4972A be more useful in analyzing local area networks. And it points out that these utilities have been tested, but they have not gone through a rigorous testing and QA program. And these tools are unsupported and are provided on an as-is basis. So that's the nature of protocol analysis that HP provides. And the predicament is that they have in here a series of some, perhaps it's 20 or so protocol decoders, and we're faced, but in a somewhat different way than with the Spider monitor, to pick which one we want to look at. Okay, there's nothing built into the system. We can look at the data in hex. If I like, I can go and somehow show the data. I've already included a filter, but basically get the data in hex and perhaps recognize it. Here's the default way the packets are displayed. go up to the top. You get a destination field, which it knows about, a source field, the ether type, and then the data. Sound familiar? Its only other concession is that you can actually tell the HP product that this is an 802.3 style network and it knows about ISO length field instead of a type field. It'll decode that one format for you. In order to break things up, we'll pick a different protocol. Let's go and use a DECnet protocol instead of TCP/IP and compare the nature of the evaluation done on these two products. Over here we have an HP 4972A. Basically, it's a portable unit, rather heavy, weighs in the area of 40 pounds, and is based on a 68,000 architecture. It's rather different from all the other analyzers we'll be looking at today because it does not use DOS, it is not programmable by the user, you can use industry standard peripherals, etc., etc. So of all the products today, it's the one where basically what you see is what you get. You use it the way it comes from HP, and you're at their mercy for upgrades and changes. So let's go and simply start using the function keys, which are along the bottom of the keyboard here, little lights here, and we will simply put it in a mode where we're going to monitor the network, capture packets, and I'll ask George to play back for us a sample trace there. There's a sample trace called DECnet DAP. We'll start the sniffer capturing. We'll start with one key press, two key presses, the HP product capturing. And at this time, the HP product is waiting for incoming frames and will now transmit on the network a sample of data that was previously captured. Press down the Alt key. Is that stopped or did it complete?
It's just one cycle. I should use...
Okay, that's fine. Just press the Alt key for the moment.
Okay. Just press Alt.
Okay, fine. Let's just stop. Fine, and we'll display. I guess that was the length of the trace. It only was 26 frames. Here on the HP unit, what you can see is its standard decode as data comes in is to show us the perhaps you can zoom in a bit and improve the focus. There we go. It's showing us in this case the destination address of the frame, the source address of the frame, the type field. Here is a number 6003, and then following that are additional data bytes in the frame along with an ASCII translation. And this scrolls by as we can see it. Now that information is available. I can now look at those frames on the HP unit. Let's go back to the beginning of the trace. Whoops. And I'm going to select frame number 7, which is here on the center of the screen. And I'm going to select frame number 7 on the sniffer. Which is here. And on the sniffer, I will go and turn on actually the hex display. While we're here, we'll turn on the detail display. And this is basically the same level, the hex information on the HP unit and the hex information and its decode on the sniffer. Now notice the sniffer, as we've seen before, in its summary line is already telling us something about this protocol. It's already said that this was the Data Access Protocol, DAP, which is one of a family of DECnet protocols. all we can see here is that this one has ether type 6003, which is generically all of the DECnet protocols, which has many, many different levels. In fact, at this point, it's just loading it into a standard Ethernet decoder, which is sort of like a sniffer without any protocol interpreters decoded. That's the nature of the stuff. So let's go and figure out how is it that HP claims that they can decode the DECnet protocol, and that's done through this information. They have these utility programs, which, as we mentioned, are provided with no support and with no warranties at all. And if I look in the section on protocol analysis here on page 4, indeed there are some things which apparently have to do with DECnet. There's one called DEC-N-MOP, DEC-N-NSP, DEC-N-ROT. And if I look at the first one, it's the DECnet maintenance operation protocol. Perhaps that's what we've just captured. Perhaps we've captured DECnet layer 4 NSP, or perhaps we've captured the next filter that they have called DECnet layer 3 routing protocol. My point is, how is the user to know what it is? What we can now do is to load a filter. We could load the DECnet MOP filter. So we're displaying the data. Let's go and load a protocol filter. I'll exit from the display mode, press a key, go to disk functions, select the volume, which I do once, the hard disk, load a file. The type of file I have to specify is a network file. Now I'm going to look in this list. It shows me 6 names at a time, and they're not even alphabetized. So I just keep looking until I see the one I want. Press other choices. I don't see it there. Press other choices again. Press it again. Aha, here's DECnet MOP. So now I press load, and it's going to load the DECnet MOP filters, which are their protocol interpreters or translators. It's loading it from its hard disk. It's now loaded. I can now exit again, and now I can say examine data. In this case, I'm going to pick a format. I have to say select format, press another key to say filter format, and now finally I can now pick one of the particular filters I like by saying change filter, and now I can specify which packet I want to look at. Now this packet, according to this, matched filter number 0, and it decodes here some fields. Perhaps you can zoom in. Byte count, dump load, and so on. The only problem is that this protocol, by the way, is not the maintenance operation protocol. The maintenance operation protocol doesn't have DECnet type 6003. I mean, I happen to know that, but this machine insists upon, since I told it that this was DECnet MOP protocol, it simply splits up this packet into some fields, labels the fields, labels the type, and I basically can very inadvertently, without trying to misrepresent the system, but very easily have it show me a packet in totally the wrong format. This is not a MOP packet. The system hasn't told it to me. I can go and say, gee, maybe it's a request program packet, and again, it decodes it as if it were a request program packet. The fact that it isn't really isn't shown here. Now, the only way that it is shown here is if I have the filter loaded at the time that I'm collecting data, then it may match a particular channel. So they may have some test set up that will match a request memory dump packet if the packet that's being sent in the network is that type. Now, in fact, the packets that we're looking at have Ethernet data, they have DECnet routing data, they have DECnet NSP data. They don't have maintenance operation protocol. Here we're faced with a bit of a dilemma. Even though we know that we have to pick either the layer 4 NSP or the layer 3 DECnet routing data. So why don't we pick, let's start at the bottom, the DECnet routing data. So I'm now going to exit once again. And I'm going to load with disk functions, load a file, network file, and the one I want is called next, DECnet NSP. So I'm going to preset the machine for that particular thing that I plan to analyze. Notice we didn't do that with the sniffer. With the sniffer, we collected the data. We then chose any analyzers we wanted, any packets. They were all loaded. And in fact, the system told us what the packet was. Notice it's saying here on some of these packets, in fact, that this was just an NSP packet, a link. This was just an NSP acknowledgement. It did not have a higher level protocol. In these cases, these packets here that are DAP packets, as you know, have a lower level protocol, which is in fact NSP, which is in fact DECnet routing. If I insist, I can have the sniffer show me that by turning off highest level only, something which we don't often do. But in fact, here we see that this DAP packet also was in fact an NSP packet. It also was a DECnet routing packet. And it also was a data link packet. And for the HP analyzer, we have to know ahead of time what the nature of the packet type was. It doesn't have an analyzer for DAP, which is a file-oriented package. And it says apparently it's got decoders either for NSP or DRP, DECnet routing. Let's load, as we said before, the DECnet routing monitor and play back the data one more time, an opportunity we don't often have in real life. But since this is a laboratory situation, Maestro, if you'll strike up a tune.
Now, should I hold the Alt down?
No, just press Enter will be fine.
Oh, that's right. DECnet.enc.
Replay, space.
Now let's out the replay. There we go.
Okay, the data came in. We'll stop the monitor. And now the idea is that now it will have recognized the packets and break them into their format. And in this case, we should see them match based on the filter of the various filters that it matched. So what I will do is select a format, and we'll tell it to use the filter that the packet matched. Now, take a look here at this first packet. See all these X's up here? That says each X represents a filter. This packet did not match any of the filters. No filter matched. It didn't match any of these filters. It didn't match any of these filters. Packet 1, 2, 3. Now, why is that? Let's take a look at that same frame with the sniffer. Packet number 1. It says here that this was an Ethernet packet 6003 DECnet data packet routing. It's a DECnet routing protocol data packet, and it was an NSP control initiate, and it was a session control connect message. It was a legal DECnet routing packet. And if we look in the hex window, there's the packet. And this corresponds to that same packet. The reason is that, in fact, in the case of DECnet, there is an optional field which we can see in the detail window where each DECnet routing packet has a length field, and then it has a packet format byte. And part of that packet format byte says in a particular bit whether or not there is padding in this packet. And if there, in this case, there was no padding, that's what the sniffer says, this bit happened to be a 0. If this bit was not a 0, then it means that there was some padding. I think possibly if we look at this example some more, nope. I think we don't find any packets in this particular trace which have any padding. The HP product, unfortunately, if we look here at we loaded the NSP decoder, I guess. We loaded the NSP decoder. Okay. We loaded DECnet NSP decoder, and in the fine print it says the following thing. The NSP message filters have optional padding at the routing level, which may be from 1 to 8 bytes in size. Most DECnet traffic we have seen that has padding bytes only has a single pad byte. For this reason, you may have to modify the filters to match the packet with or without padding. In other words, if you happen to have exactly 1 byte of padding, this filter will work. This particular traffic, which was taken from DECnet DOS, doesn't happen to have any padding. It has 0 padding bytes. And this protocol filter was set to, in fact, assume that there is a padding byte. That's why the data match no channel. Now we know that this happens to be a data packet, a data segment, and here's the case I'm trying to give you. If I tell it now that by pressing this key it is a data segment packet, in fact then there's this byte here called optional padding. Well, there really is no optional padding byte. Okay? There is not an optional padding byte in this packet. This packet happens to have 0 length optional padding. For me to fix this, I have to now go and edit this filter to fix it. By the way, not just this filter, I have to edit the other 15 filters, which are here at level 4, to also correspond to 0 padding bytes. Well, if I knew that, why do I need a protocol analyzer is a question I would ask. Secondly, we can load another trace, which is also taken from a standard example, where the traffic from station A to station B uses 0 padding bytes. The traffic from station B back to station A happens to have 1 padding byte. This is also an example of DECnet DOS running on some other configuration, which for some reasons of configuration or programming chose to have the padding the other way. Clearly, you cannot have both circumstances loaded in the HP analyzer at the same time. All right, let's go back to this example of DECnet. In this case, the NSP level, the way that it's been programmed here, comes with an assumption that there is 1 byte of padding. Let's now look at the routing level. And to do that, I'll keep the same data, but I'll go back and load from disk a file that is just the routing level. Okay, now unfortunately, in order to analyze this data and make use of the filter matches, we have to go back and replay the data again. I mean, this is one of the unfortunate designs of the system, that at this point I can reload my filters and I can tell it, use this format, use another format. I can select the format I like. But if I want to go back and use whatever ability this has to tell me which of the 16 different packet formats this might happen to be, okay, it doesn't have a replay mechanism or a refilter mechanism or a rematch mechanism, whatever. In this case, we're going to have to go back and actually replay the data. Either that or we guess which of these protocols it matches, and there's no way to know if it's right or wrong. So fortunately, again, we can replay it. So I'll go back, exit from this, and monitor network. If you can just press F3 and restart that. Okay, we've recollected the data. I'll stop the monitor. And here we notice that packet number 1, according to this, matched filter number 0, and it selected that, and it says that that is a data packet with a destination area, a destination sub-area, destination ID, etc. Service class, protocol type 0. Let's compare that same information on the sniffer over here. Packet number 1. It's decoded a length field, which is not shown at all in the decode of these fields. The length is actually in the packet. If I look carefully here at byte offset 15, this 3400 happens to be the actual length field in the data packet. The sniffer, that's easy to see. I just go and select DECnet routing, the data length field. There's 3400. That simply is not being decoded in the HP unit. Then it comes back to this field, decodes all of the fields in it, all the various options. Doesn't decode the packet type. Area and sub-area are decoded the same. And now let's take a look at the destination ID. Notice here the destination ID is 1.255. On the HP unit, the destination ID is AA000400FF04. Those 6 hex bytes. And again, if I go to the sniffer, put my cursor on this field, it would highlight those same data. The difference is that the HP unit has no more capabilities ever in its analysis than simply giving you a sequence of hex bytes. That is a fundamental limitation to the analytic capabilities of the HP filters and so on. In this case, the protocol interpreter chose to display this in a form that a DECnet user understands. He knows that that is Area 1, Substation 255, whatever the terminology is. That's the traditional DEC way of writing it that's in all the DEC manuals. This number, means something to people who might or might not know what that is ahead of time. And that's a typical style. Notice it only decodes a certain set of fields, and so on. Well, in a sniffer, if we simply go ahead and continue, let me just point out that we have, again, at the network services level, comparable kind of sophistication in terms of decoding more fields. And finally, in this case, the session control level, many fields are decoded, and in particular here, it's real clear that we have things like a descriptor length field, which is length 9, followed by the 9 characters that are being transmitted in that packet. You can imagine if this length was 6, this would be 6 characters long. This type of protocol, which is very typical throughout virtually all of DEC's protocols, this style of a length followed by a variable length string, followed by some other character and a variable length string, simply cannot be handled in a fashion of fixed length offsets, fixed length styles. You either have to know ahead of time what the length is and program for it. Let's move on now and look at the Lanalyzer. The excellent Lanalyzer unit, and what we'll do is pretty much go through the same activity. It also claims to have DECnet analysis. Why don't we transmit that same data and capture it with the Lanalyzer? So let me start start the analyzer running. And we'll replay the data.
Okay.
Go ahead. Okay, the data's been replayed. In this case, we're using the default setup. All those packets were collected here in one filter called promiscuous, which basically means it collects all the packets. Okay? And we'll see in a while how we can set up a different set of filters that collect a subset of the data specific for DECnet, but at the moment we'll just look at the promiscuous one. I'll stop the trace going, stop the trace, and at this point ask it to display the data for me. But the first thing you see is a display very reminiscent of what we saw first on the spider monitor, first on the HP analyzer, and now on the analyzer. Basically a packet number, a length, time of day, which by the way can also be changed to the time from the previous packet, delta time. You have a choice of one or the other. Destination and source addresses in hex, which all of these products will substitute a symbolic name if they have it in a table. And in this case, simply the ether type. Not a symbolic name for that. And it happened to match, again, channel number 1 was matched. Contrast that to this summary level from the sniffer. It can provide virtually the same style of information to the left-hand side of the screen. The right-hand side of the screen is radically different. It doesn't just say 6003 or DECnet, but in fact is showing you that this is a session control protocol, NSP, DAP. If there was TCP/IP here, whatever there was would show up here, as well as a number of very significant parameters get printed out, as we've seen before. Window sizes, types, file names, etc. get shown to you immediately. Coming back, here we simply see, at this level, one number, an ether type. Well, let's move ahead and ask the system to provide a further, more detailed decode of that. We can look here in function key 6 at packet data. And in this case, we've told it to display data. And here, in fact, it is showing us some Ethernet-like information, the length of the packet. It matched this promiscuous channel, the source and destination address. It, in fact, was a DECnet routing packet. The routing message length was 52. And then it proceeds to decode the flags, area, sub-area, destination ID. Boy, this looks awfully familiar. This is very, very close to exactly the information that we were seeing in the sniffer. Let's compare it. We go down here. It goes into the NSP level. And it says it's a connect initiate. Connect initiate, segment size, and then stops. Whereas the sniffer continues to what are, in fact, higher levels, application level protocols above a transport level. NSP is a class of a transport level like TCP, and the network general protocol interpreters typically go up to a user application. In this case, it's session control protocol was decoded here, and the analyzer simply stops at that point and just says plus data, plus excess data. If we go here, for example, to packet number 7, packet number 7 was the packet that had the DAP protocol, the file access protocol, saying what operating system was being run and buffer sizes and so on. If we try and do that here, we go forward to packet number 7. Again, it decodes the transport level, but does not decode the higher level protocols. The same is true for virtually all of the other applications within TCP/IP. The same is true for XNS, SMBs, and so on. Now, there was recently released by XLN a thing called an application library, and it is claimed that the application library decodes high-level protocols like NFS, SMBs, and so on. And the way it works is rather reminiscent, in fact, I would say virtually identical to the method that we saw with the HP. They are a pre-programmed set of filters which match certain rather well-specified packets without really optional fields and optional padding, and will do some formatting similar to what we've seen now. So let's take a look at what we have for DECnet and see how useful that would be. So we can load their DECnet protocol interpreter. Okay, and this is well, in fact, I won't even do it because I'll tell you what it loads. It basically simply decodes into 8 different categories whether or not it's a DECnet routing packet, or a DECnet LAT packet, or a DECnet remote packet, and so on. And it really will provide no further additional decoding. Let's load it and run it, at least see what it would be like, so we get a good feeling. I'll go to my setups and load a setup called RX DECnet. I believe, by the way, there's no way for the analyzer to show me the names of the files, so I had to type it in from a list. Notice in the case of the HP, there was a method to at least step through 6 files at a time, albeit unalphabetized. The sniffer gives you a long scrolling list. So here we've loaded it, and now it has 7 filter channels set up: dump, remote, route, lat, diag, SCA. So this is apparently the DECnet interpreter application library. If I now say run, if you'd play that back again, George. Okay, it's told us that it just received 26 packets, and they all were DECnet routing packets as opposed to LAT packets. Okay, so all 26 of them were in that, matched that particular category. And if I display them, there really is no additional decoding available. Now, the predicament is the following. If I look now at, let's look at another protocol. Let's look at the NFS protocol. That's a very popular TCP protocol. So let me set up the analyzer to decode NFS packets. Well, tell you what, while we're here, why don't we tell it to decode SMB packets? That seems even easier. So I'm going to load the analyzer's SMB decoder. Which is called SMB function. Start the sniffer. George, I'd like you to play back the file called DEC SMB. Oops, let me start this, excuse me.
Okay, now?
Now please. All right, is that complete there? Okay, now what I will do is stop the sniffer. Let's turn on a protocol filter here. I just want to see SMB packets. Let's see if in fact there were any SMB packets in that trace. Okay, sure enough, there were a bunch of SMBs. There was a read, okay, read 2 bytes at some other location, okay, read 63 bytes. These 2 stations were running SMBs. If I look in the analyzer, in fact, what happened was it had no packets were saved in its buffer because none matched the 8 different channels that they have. Check directory, get file attribute, open file, create file, write a block, read a block. These were read block commands, and it didn't match them. I will leave the mystery open for a moment as to why it didn't match them. I'll leave that running. George, I'll collect traffic again here. Would you play back the file that says 3com.enc?
You have a new operator. It's Renita 1.
Thank you.
Aaron?
Yeah. Go ahead. Okay, we collected some 55 packets there. Again, we have no packets so far that have been collected by the analyzer. It's seen 129 packets or so. None, however, matched its filters. Let's take a look at those packets. Press stop and display. And again, here are SMB search commands, SMB open command, SMB read command. There are SMB files. There are SMB packets there. Start collecting again. If you would replay a file called, I believe, TCP NETB. I think that has some more SMB commands in it. TCP NETB.enc. B. Okay, we have some frames. Stop, display. There are some SMB commands. Writes, closes, directory searches, etc. In this case, in fact, the analyzer found 2 open file commands, 2 close file commands, and 10 write commands, and 4 read commands. So it did recognize a few packets in that case. Let's try some additional examples. Len, could you change to the other directory? Let's go ahead now and play back the file called HPSMB. Okay, assuming that was it, let me stop and display this one. Sure enough, there are SMB frames, and none of them matched the filters here. Let's continue on. I'll put this back into capture and play back ATT-SMB. Okay, we have some packets there. Aha. There are some SMBs. Again, create searches, writes, etc. 0 matched here. So far, we've seen 1, 2, 3, 4 traces which have SMB protocols, but in fact, the analyzer with the SMB application library hasn't seen them. Well, I won't keep you in suspense. Let's play back one more. The TCP NETB file. All right, let's take a look at that file. All right, no surprise. There was a write command, close command, search, etc. And finally, here we actually see some packets that matched an open file command, close file command, write block command, etc. We stop the trace. Let's try to understand what's been happening. Why is it that the sniffer saw SMB commands, SMB protocol in all these different places, and in fact, the analyzer did not decode it? The explanation is fairly simple. It has to do with the fact that all these different SMB commands, which is an application level command, were all on top of or being carried by different lower level protocols. 3COM, for example, the first one we looked at, uses XNS lower level protocols in order to transport SMB DOS file sharing commands. HP uses a different protocol. AT&T uses an ISO protocol. And what this means is that they have a perfectly valid SMB command. When it was decoded, it looked to us exactly the same. But put another way, they're not at a fixed known offset in the packet. Where the SMB command is depends upon other parts of that same packet, so-called lower level protocols. And in fact, those lower level protocols not only vary from vendor to vendor, they are in fact variable in length. They're not at a fixed offset. In fact, in the final case we ran of SMB commands on top of TCP, that particular case, the SMB commands are at a constant known offset. And that offset was recognized by the analyzer, and it was able to recognize those as SMB commands. But it only saw a few percent of the actual SMB commands. It did not capture the SMB commands. And it's fundamentally not capable of doing that level of filtering or analyzing. Notice also, by the way, that what it's doing here is to categorize them into 8 categories. I mean, you get to pick 8. Spool file, which was one of the things we saw go by there, spool file command, print spooling, wasn't one of these 8 that are programmed here, so it wasn't captured. And again, we're forced into a limited set of possibilities. Let's take a look at these packets now that it did decode them. See what they look like. Again, at the summary level, we don't get much information as to what the command was. The sniffer, we can see reads and writes. We can see here that this frame was an open file command. And if I look at the detail of that open file command, by pressing one key, I can see the file name. It was being accessed in a shared open mode, so other users could access the file. It was being opened for both reading and writing. Various directory search options. So we look at the following frame. The file was open. This is the response to the file open. And here it gives me a whole bunch of information, including things like the creation date and time of that file. I want you to think back. Remember, we saw the creation date and time of an NFS file on TCP/IP. The internal format of this date and time has nothing to do with the internal format that Sun Microsystems uses for their date and time. We don't care. As users, we don't care. This was 3rd of December, 1987. We can understand that. Let's take a look at the packet decoding of the analyzer. We're looking at frame number 1. Here we're looking at frame 65. Let's go to frame 65. Compare the same frame. I'll say go to and type in frame. Well, I guess it's not called 65 here because we're actually not collecting the same subset of frames. It's not capturing all these frames. We're going to have to figure out. This is frame 1. And frame 1, I can see here, match the receive channel of right block. Zoom in. Okay, this was the first one that matched was a write command. Okay. In fact, it didn't capture this first packet. It didn't capture low-level packets. The first packet the analyzer captured, what we have is our fifth packet in the buffer, is this write command, SMB. So let's go to that one, and let's look at what we see here. There's a write command. Here, we're seeing at the top of the screen the Ethernet and IP and TCP decoding. That information can be expanded to more fields. We're going to focus on the high-level protocol. And here we come down to the SMB decoder. And this is the analyzer's application library decoder. And here it's telling us that the SMB function was 0B. That's here. Function was 0B, which is write byte range. Okay, that's why it matched write block, write byte range. Has some other parameters, which basically you sort of have to guess what these fields mean. There's a return code field, which has to do with whether or not there was an error message in the return. In this case, it was being decoded. Said, okay, if we had an error here, and we can bring up an example where we did, where it couldn't find a file, we would see a full text explanation. In this case, we're going to see just a number that wasn't 0. That's all it can do. At this point in the SMBs, it just so happens that all of those fields are always in fixed offsets and fixed lengths. Those are exactly the same. Unfortunately, in the SMB decoder, following that, all the fields are variable length. They don't have any fixed structure. They're variable length strings, variable counts of data, and so on. And the sniffer was able to decide that the number of bytes to be written was 33. It was at offset 128 in the file. And by the way, here are the remaining 33 bytes that are being transmitted. That is simply not present in the decode here. We can look at the next file, the next packet. It's also a write. We're looking for the first one that's not a write. Okay, here's a close file command. Just match the close file channel. Let's find our close file command. That's over here. Another way to find that, by the way, is, notice I can say search for the text close. And it found that file for me, that frame for me. And the file is being closed. In this case, in DOS, when you close a file, you give the date that you would like to have recorded in the directory of that file, the timestamp that it should be recorded in, so that when you copy a file, you can give it the original date that it was originally written before the copy. Again, we get some list of parameters, and then, bloom, data. What is that data? Well, you can guess what that data is. Well, actually, that data, that data is the process ID. I thought I was going to tell you that that was the date and time in the packet. I was about to look for this field, which is, again, a difficult field to decode, this EA33B3. Notice what it is, in fact, highlighting is this field here, 9E17, which is, in fact, a process ID. And it claims that it's data. The process ID, it thinks, is some value 0 up here. This is what's known as a bug. This is known as an error in the SMB decoder from the analyzer. And we can go through and try and match up all these fields and make it work out. But they're not using a correct version of the SMB decoder. At this point, I'd like to stop and hope I've given you enough of a feeling for the radically different nature of the way protocol decoding is done between the sniffer, which I think is clearly in a unique camp. It basically has the ability to take packets, and it's doing two rather remarkable things with them. One is, it is decoding the packet based on what it sees in the packet, lets you know that at a very high summary level, does that in a way that has a lot of information about all the different ways these protocols can be packaged, which one calls another, which protocol calls another. It found SMB packets in 5 different contexts, managed to decode them. It knows about subtle things like optional padding bytes that may or may not be present, that may be 0 bytes long, 1 byte long, 8 byte long, and other kinds of, I almost shudder to use the word sophisticated. I mean, that's in fact the way protocols are. They're not sophisticated, that's just everyday protocols. There's nothing more advanced about a protocol that optionally has padding bytes in DECnet. Every DECnet packet has it. This is life. All 3 of these other network analyzers have as their protocol decoder something which more or less is wired into an assumption of fixed length fields, fixed offsets, a hex decode, possibly the ability to translate it into decimal instead of hex, and really no real knowledge about protocols. And finally, they're not really open to the user. I mean, the interesting thing about the sniffer is that all this decoding is being done by a program that can be modified, that users can write themselves. It's not a closed system. You can expand it. It can be extended. In fact, you can even call these protocols one from another. If someone is developing or has some unusual use of, say, an SMB protocol, one could write just a portion of a protocol interpreter which then used the internal sophistication of the knowledge base, I'll use that word, of the SMB decoder that's available with the sniffer. That kind of encapsulation of knowledge isn't present in just the architecture and design of these other products. It's very hard to imagine how, without really redoing them, they would be able to have that same approach to protocol analysis. So I think we're here looking at 3 products in one camp in the sniffer. Very sophisticated product, very advanced product in knowledge of protocols, encyclopedic, that's in a different league. With a sniffer, if you have a hypothesis about a problem, okay, let's say you believe that you are not sending ACKs frequently enough. Okay, you believe data is being retransmitted too often. Or you believe that, in the case of SMBs, a user is reading too small, very small portions of a file. Or you believe that someone is locking a file incorrectly. I think you could realize that with the sniffer, your strategy of solving that problem would be, gee, it's easy to see whether or not those things are happening. How would I do that? I'd connect the sniffer up to the network. I'd set a filter to look at traffic from this particular user to a server that we're looking at. I'd collect some data. I'd press stop. I'd look at the summary display. And from the summary display, I mean, in a matter of seconds, I would see, is the user locking the file? is the user reading large records or small records? Here this user is reading small records. He's reading them near each other in the file. Okay? I can get that information in literally as fast as we did it here in a matter of seconds. It is not clear to me, first place, that any of these other products could answer the range of questions that we had without knowing a lot more about the protocols. That is not contained in these products. That is not contained in the documentation you get from these manufacturers, even with all the quibbles they give. And even in those cases where it does have the information, where maybe it knows about TCP acknowledgments and so on, it certainly would be a process of hours to track down a hypothesis like this and convince yourself whether yes or no this problem is happening. It just doesn't lend itself to that very simple, let's go see what's happening, find the problem, and resolve it kind of strategy. And I would say the difference is dramatic in capabilities. That is, in one case you can do things in minutes that with the other products either they couldn't do, or if they could do it, it would take many, many minutes, hours to dig out the same simple fact.